It's the Friday night double feature. I'm going to be giving two lectures in a row, and we'll see how it goes. So last time I gave you an overview of sort of how I like to think about active systems, what interests me about them, and gave you a bunch of biological examples. And in particular, one point I wanted to put some emphasis on was the idea of active materials. And the key idea there was that what I mean by an active material is simply an active system that is homogeneous in space and time so that we can define material properties, things like density, stiffness, and other sorts of things make sense. Okay? And I gave you a number of examples of active materials in biology. Uh, yeah, so in biology, we found that activity could affect not just the noise spectrum, and the way we saw the noise spectrum was by looking at the diffusion of passive particles, but also the material properties. And in particular, I told you about some experiments that were done in cells where Guo found two different contributions to the activity affected the cytoplasm in different ways. Okay? So in particular, he focused on the contributions of myosin. That's a protein that hydrolyzes ATP to do work. And he and his co-authors found that when he changed the activity of myosin, he found a big effect on the rheology of the cytoplasm. Okay? Didn't really have, it had a significant impact on the noise, but it didn't have a huge impact on the noise. Whereas all the other ATP dependent processes in the cell, all of them, didn't really do anything to the properties, but had a huge effect on the noise. Okay, so those were that was where we wrapped up last time. Well, not quite where we wrapped up, but that was sort of the end of the meaty discussion of last time. What I want to do next, well, I'll tell you a little bit about what the plan is for the rest of today and for the rest of the lectures. For the bulk of today's lecture, I want to focus on metabolism and how we quantify it and how to think about it across scales. And then later I want to raise some important issues in transport phenomena that impact the plausibility of actually making active materials. But for now, before I move ahead to metabolism, I sort of want to wrap up this idea of this concrete example of how activity can affect material properties by talking about an experiment that was not done in a cell, but was done with the materials from the cell that were hypothesized to play a dominant role in the material properties that were affected by activity. So if you recall, the model system for this in vitro experiment, what are these squiggles? Anybody remember what these are? Actin, great. And the actin is cross-linked with two different types of crosslinks. There were the boring passive crosslinks And there are a few different types of crosslinks you can use. In the experiments I told you about at the end of the day yesterday, it was alpha-actinin. In the experiments I'll tell you about today, the passive crosslink was something called filamin. The detail, they actually have some pretty interesting differences, but that's beyond the scope of what we're talking about today. And then, the exciting part, or the active part, were that there were also crosslinks that were formed by bundles of non-muscle myosin 2, which I will just, for now, just call My2 as an abbreviation. And the key thing about these crosslinks is that they consume ATP to generate transient force dipoles. Okay, so yes? Yeah, so they definitely pull on it in a way that is not isotropic. There is a well-defined orientation of the bundle and how it connects to the two filaments. The details are beyond my knowledge, but it's certainly not. Well, if you look at the disordered network as a whole macroscopically, the stress, if the network is disordered and doesn't have any liquid crystalline order, then the net stress that's generated is isotropic. But microscopically, each of the individual crosslinks is very anisotropic. But the details of how it's anisotropic, I don't remember. Thank you for asking the first question today. The first question is the hardest. Okay. Yeah. So, in the presence of ATP, these things will contract. And as I mentioned yesterday, if this network is not constrained, it will just pull itself down tremendously. I quoted a number of 64 times volume reduction, but you can get more or less than that depending on the composition. And also I mentioned that if you restrain, or I showed, if you restrain the system as is trying to contract, it can do work on its surroundings and deform its surroundings. Okay, so the question I want to address is, I just want to discuss briefly what is the actual mechanism. Can we understand the mechanism of how these changes in the cytoskeleton with activity affected these results that Guo and Waits had, that they saw when they changed the myosin activity? They saw a pretty big change in the properties. Okay, I want to explain the physical mechanism for that because it's rather elegant. So how does the ATP hydrolysis change the properties? Okay, so the properties that they measured in the in vivo experiments or in the cell experiments were mechanical properties of the network. The macroscopic analogous property you would measure would be the rheology. Okay, and so the core hypothesis about why myosin plays such a big role in changing the properties is because the rheology of these actin networks is highly nonlinear. Okay, and I'm going to explain that. Okay, so the rheology of semi-flexible polymer networks is nonlinear, and it can be very nonlinear. Okay, and so there was a nice review paper that just came out recently by Brodertz, I guess his name is, and McIntosh. I'm not sure which journal it actually showed up in eventually, but it's on the archive. It's a really nice, very, very thorough review of the rheology of semi-flexible polymer networks. I mentioned yesterday, but maybe if someone could remind, other than me, could remind everyone, what do I mean when I say the polymer network is semi-flexible? Mm-hmm. Exactly, yeah. So that's exactly like he said. and somewhat like I drew in the picture, right? So that each of these polymers of actin has a persistence length, and eventually, if you zoomed out really far, it'd be a fractal network. But at this length scale, they're pretty straight, and the distance between the crosslinks is comparable to the distance at which they start feeling thermal fluctuations. And so the key point here is that the rheology has contributions both from the thermal fluctuations as well as the bending rigidity of the filaments themselves. Okay, and I won't get into the mechanisms of why that is, but I want to describe to you, since I'm an experimentalist, how one characterizes the nonlinear rheology. So the key thing in a rheological experiment always is to apply a stress. Okay, and McIntosh, with previous work with Waits and Gardell, introduced a sort of a funny but really nice way, I think, of probing the nonlinear rheology. So normally you would apply either an oscillatory stress or a constant stress. What they introduced maybe 10 years, 15 years ago now, was that they would apply a DC offset stress, and on top of that they would apply a small amplitude frequency-dependent stress, and then they would measure the strain, which of course has some zero frequency offset, as well as a small harmonic variation at the same frequency as the applied stress, assuming that these perturbations are small enough. Okay, and so then they defined this new rheological quantity. Basically, I think they call it a differential modulus, where they just take the ratio of the stress and the strain. But of course, these are all complex quantities, because in an oscillatory test, you have to keep track of not just the amplitude of the response, but also the phase. Okay, this is falling. There we go. Okay, so that's their quantity. Okay, so and the important thing is that in the limit, as you make the offset stress go to 0, this K of nu goes to the classic complex shear modulus that you would see in a regular experiment. Okay, so if you make one of these networks and you put in the actin and you put the filament in and you put ATP. This is sort of this. For technical reasons, you might have expected that if they want to see the effective activity, they might put in actin, filament, and myosin, and then sort of slowly increase the amount of ATP. But if you only have a really low quantity of ATP, what happens is you can run out of ATP, and so you don't have a time-independent phenomena. So practically, it's actually simpler to to have actin, filament, and ATP all at fixed concentrations, and then slowly titrate in or introduce more and more amounts of the active crosslinker. Okay, so in the case where there's no myosin, okay, I'm going to go back to drawing data. Okay, so we're going to show the real part of the differential modulus as a function of the applied stress, or the DC offset, or the constant stress, and the range of the stiffness is going to go from 1 to 100 Pascal, and the time scale is going to vary from 1/10 of a second to 10 seconds. Okay, and in the case of no myosin, what they find is for values of the pre-stress or offset stress less than about 0.1, that the K prime has a constant value, which means that the response of the system is still linear. But somewhere between 0.1 and 1 Pascal, the sort of goes up to here, like that. The modulus increased dramatically as you increased the pre-stress. Okay, so so here in the absence of a pre-stress, the modulus was only about 1 Pascal. But when they added a pre-stress of about 10 Pascal, the modulus was as high as 100. Okay, so it increased by a factor of 100. Yes? It is not. And so this is actually something that sort of drove me nuts in looking. Oh, I forgot to write down the reference. This morning, this is someone's name who I can never spell correctly. So the reference is here, 2009. Okay, so in the text of the paper and in the figure caption, they never mentioned the frequency that they did this measurement at. And it's okay though, because if you go back to the previous figures, it's not okay. They should have said the frequency, but they can sort of get away with it because all the rheology they showed in the previous one was power law. So like all the scaling you would expect wouldn't really depend too much on the power law in the frequency. So maybe you could argue that the frequency doesn't matter, but one should always just report the frequency. So some finite frequency. I bet it was order 1 hertz. That's what I bet. Good catch. Okay, so yeah, so this stuff really stiffens. Okay, and this is actually a special. Such dramatic stiffening is really a special feature of these semi-flexible networks. Does anybody know the hand-waving explanation about why such a network is so strain stiffening? Yeah, exactly. So that's the basic point. So the idea is when in this regime, where the rheology is, the modulus is strain independent, what you're really doing is that most of the response is you're really just pulling out the thermal fluctuation. So it's an entropy dominated response. And as you apply more of a pre-strain, you pull out the thermal fluctuations, right? And then you're really directly bending or stretching or deforming the filament. That's my hand-wavy explanation. If you really want to know how it works, read this very long and detailed paper by McIntosh. Okay, but that's the basic idea. So okay, so this is what the rheology of the network, the basic semi-flexible polymer network, looks like. Then what they did was they added myosin. Okay. So, and what they measured is they measured the stiffness, G prime, so in the limit as sigma 0 goes to 0, with increasing myosin 2. And so here I'm going to plot the modulus at some frequency. And that's going to vary again between 1 and 100 Pascal. And now on this axis, it's called X. It's a dimensionless number. Okay, it's the ratio of the concentration of the myosin to the concentration of the actin. Okay. So just roughly speaking, how much myosin did they put in there? And they go from relatively low, and I would say reasonable concentrations of this crosslinker to pretty high to sort of crazy high concentrations of myosin, actually. And what they saw, 0.0, yeah, that should be 0. Thank you, 0.01, thank you. Yeah, so 0.1%, 1%, 10%. Okay, it's hard for me to, the reason why I said it's crazy high, it's hard for me to imagine a network where the crosslinker has a concentration that's almost as high as the monomer, right? And it's especially surprising to me considering how smooth the curve I'm about to draw you is. So they basically see below a concentration of 0.001, there isn't really an effective myosin, and then by the time they get to about 0.1, the modulus increases up to 100 Pascal. Okay. So here, this is not a nonlinear rheological measurement. This is a conventional rheological measurement. And the idea, right, is that somehow, well, I haven't explained yet, but I'm about to on the next plot. The basic observation is you have more contractility, you have more stiffness. Now, if we go back and do the same sort of measurement that we did of the nonlinear rheology as a function of how much myosin we have in, there's a pretty clear picture that comes across of what the underlying physics is. Find some good chalk, some good colors rather. Okay, so here I'm going to write the concentrations of myosin, right? So for this yellow curve, it was basically indistinguishable from 0 myosin if x was less than 0.001. If they had an x value of about 0.005, though, they started to see a big effect. So this is x equals 0.005. And then for one last color, this will be x equals 0.02. Okay. So if you read off the value of k prime at small values of sigma 0, that should match the values I wrote I drew here for the modulus on the right-hand side, because of course they're the same thing. So we already knew what these were going to look like. But the interesting thing is that by the time you get to really high strains, pre-strains, the myosin doesn't really make a difference anymore, right? It really only seems to make a difference at the lower values of the pre-stress. So for each concentration of myosin that they look at, they need to go to a higher and higher pre-stress before the nonlinearity kicks in. Okay? And so ultimately, the interpretation, and I'm offering this without any derivation or even experimental proof, but I think this is a plausible interpretation of this data, is the idea that when you add the myosin to the system, it puts a pre-stress in the system. That's equivalent to the sigma 0 that they were applying macroscopically. Right? So in the last lecture, I explained to you how the myosin can take the gel and it can contract it. It can, or if you take the gel and you grab onto the ends of it, it will pull on you, right? The gel pulling on the outside world is equivalent to the outside world pulling on the gel in terms of the stress state inside of the gel. So the point here is that when you have a myosin concentration of about 0.005, you create a pre-stress on the order of 1 Pascal, and when you have a myosin concentration on the order of 0.02, you have some higher pre-stress. And the external stress that you apply doesn't really do anything until to the nonlinear rheology, until it beats the nonlinear rheology of the internally generated stress from the myosin. Yeah, exactly. So I do not, I don't know. I can guess what they would say. So I think one of the important things about about my guess is that it would really probably just like it look like this the whole time, because in order for my understanding is, or in order for myosin to actually form to act as a crosslinker, it actually needs to be turning over ATP. But I might be getting that backwards. Am I getting it backwards? Yeah, I get the rigor mortis thing, yeah. So if it's already bound, it can't come off in the absence of ATP. But I don't know if it could get on, right? It might not be able to get on either. So it might. So yeah. So I'm not really sure what happens in that limit, and it's an important limit. It's probably in the supplement of that paper. Yeah. 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 So, my understanding is that in the case of the filament, in these experiments, they never go to stresses large enough where the filament unbinds. But one thing that, from my understanding of, and this is where the details of which crosslinker you use really matter. So actin has all sorts of different crosslinkers. If I remember correctly, filament, when it crosslinks, different crosslinkers like to form different geometries of the crosslinks. So some of them like to make the actin bundles parallel, and others like to have them come at some angle. Some of them are relatively floppy, and some of them are relatively rigid. Filament, as you can probably guess from the name, is the one that tends to promote actin to bundle, so to make filaments of actin. So it likes to cross-link them in a parallel sense. I don't have a sense though of how flexible it is, but because it's such a big molecule compared to a classical crosslink, it's going to be a pretty floppy crosslink. Uh, did I hit the things you were? Did I answer your question? Yeah, yeah, yeah. Yeah, in the picture that I've heard all of the authors of these papers speak about this. They never invoke any special property of the crosslink except the topological constraint, like you would in a normal cross-linked polymer network. Yeah. Yeah, what's the point of having the passive crosslinkers? So I think what happens is if I remember correctly, actually I'm sure what happens. I've seen experiments, and there's some really nice experiments by Margaret Gardell and Michael Morell, uh, where they do this. Is they'll make an actin network, and the only cross-linking they have is myosin, and the thing just completely collapses on itself. I mean, it just completely collapses, yeah, into a dense network. So you can, so if you, and so that's a nice, so that helps, thank you for asking that question, because it helps sort of make clear this idea of how the myosin can create a pre-stress in the system that's pre-straining the network. Because the myosin wants to collapse the network as much down to, close packed actin, but at the other hand, the filament wants to sort of, it has a preferred shape, because it's an elastic structure. And it's the competition between the myosin that wants to totally collapse it, and the filament, which has a prepared size that creates a stable pre-stress. Yeah. Why does it not add up? I mean, I think the point here is that this is a logarithmic scale here, right? So if the internal stress that is generated is, let's say, order 1 Pascal, right? If you've only applied zero point 0.1, it's negligible, right? It's relatively small. So, and this modulus is much smaller than this. So you can imagine if you want, yeah, I think it's just that it's the idea is that in this region, the pre-stress, internal pre-stress is much smaller than the externally applied one. But they also have a different nature too. So that's, I think, so that one thing is there's a difference in magnitudes. There's also a difference in because stress is a tensor, we often forget that, right? So when you apply a stress macroscopically, you're applying a pure shear, right? In this case, in a rheometer, but the stress that the contractility of the myosin makes is a contractile, more isotropic. The stress tensor is all along the diagonal to the myosin, and then it's on the off diagonal for in the rheometer, and so that could also might also be relevant to that. Okay. Cool. Okay, so we're done with actin. All right, so before moving on to discuss metabolism, I want to just point out some other cool model systems, sort of biophysical model systems that you might enjoy reading about. And also, I want to give you a sense of their diversity. So there are so many biological materials, but not, only a few of them have people had a chance to look at sort of the active materials in tons of detail and to provide some insights. Really so other examples of active materials, which I don't have time to tell you about, that are worth reading, okay? Probably the most important one is an example of a 1D crystalline system. I mentioned this system last time. Anybody remember what the 1D crystalline active biological material was? Muscle, yeah, exactly. Skeletal muscle. And sort of one of the most famous biophysicists of all time, named Huxley, did a ton of work on this in the 1960s, and he's got a nice paper in Science from 1967 that sort of tells the whole story from the beginning to the end, and it's really nice. It's a really nice paper. I want to go back myself and read it more carefully now that I know more in light of sort of modern stuff. But all the key ideas are here. Another old example, but not as old, only 20 years old. This one is really close to the actin networks we were just talking about. So another example of a disordered network. So it's been actually, even this model system goes, the system I'm about to tell you actually goes more than 20 years, probably 40 years back. And it's a system of fibroblasts and collagen fibers. Okay? And it's very analogous to, I'll use that symbol for analogous, where the fibroblasts are sort of like the myosin. And of course, it's not perfect, but the basic idea, the collagen fibers are like the actin, but everything's sort of scaled up. So collagen is actually quite a rigid polymer. It's not semi-flexible. It's like, it's I don't know what you even call such a network where all the fibers are pretty, there's no significant thermal fluctuations. And the fibroblasts, what they do is they are living cells. Fibroblasts are cells, and they actually serve as the crosslinks between the collagen fibers, and they pull on the collagen fibers in the same way that myosin 2 pulls on actin. And like I said, there's been papers like this for 40 years, but my favorite one of them is a paper by Brown and Prajapati. I'm guessing is maybe how you say it. Anybody want to correct that? In 1998, so it's relatively recent, only 20 years old for this system. And what's really cool about this paper, which I really like, is they introduced a fun idea which they called homeostatic tension. And it's really beautiful. So what they did is they have this sort of macroscopic gel of collagen, and there's cells in it, and the cells, contract it just like the myosin contracts the actin, but they grab onto it with a tensile tester. So they grab on it to two ends and they pull a little bit, and then they just hold They hold the ends of the tensile tester fixed and then just watch what happens. And what they find is that eventually, no matter if they, eventually the force that the fibroblasts and gels generate is always the same. So let's say they start off, they grab it at the two ends with 0 tension. Over time, the tension increases to some value around 10 kilopascal, and then it plateaus at 10 kilopascal. If they stretch it a little bit and go up to 20 kilopascal, after a little while, it goes back down to 10 kilopascal. If they compress it and put it under a compressive load, first it will stop being compressive, it'll go to neutral, it'll go up to a tensile load of 10 kilopascal. So they showed that this very, very simple macroscopic two-component system of collagen fibers and fibroblasts has some internal set point of a preferred tension. And it's really what I love about it is that it's a material property. It's a Pascal. It has units of Pascal, right? So it really suggests that if you take smaller, I would like to see if they tested it as a function of system size. They suspect that this stuff is a real material. And then there's all sorts of other beautiful examples. I've got some more recent ones, but I think you probably know all the recent ones. It's more important to emphasize the old ones, which fewer people know. Okay. Any questions or comments about those other examples? Yeah. Yes. Yes. Oh, really? Let me think about it. Yeah, I know Jean-Francois Joanny's stuff. I actually knew about Jean-Francois's stuff before I knew about this. And when he first explained it at the Gordon conference in 2009, I'm like, that's the coolest thing I ever heard. And so the basic idea of homeostatic pressure is that it's like osmotic pressure for cells, for a tissue. You grow some cells in culture, right? And you push on them, just like you would push on an ideal gas, right? But the key thing is in pushing them with a piston that is impermeable. You do it with a permeable piston so all the nutrients can get in and out. And the question is, the idea here is that if you apply a certain force or a certain pressure to this system, it will keep growing until the point where it pushes up to a certain point where it can't grow. Sorry, if you hold this fixed, rather, the cells inside will keep growing until they reach the homeostatic pressure, and then they'll stop growing. If you push more than that, they will actually retract. If you have less than that, they can basically grow forever. And the hypothesis, which was super exciting, is that maybe cancer cells and tumor cells have a higher homeostatic pressure than healthy cells, and that's why they expand. So now that I've explained this, I sort of see the difference with this homeostatic pressure of Joanny and this homeostatic tension of Brown. And I think at some level it's similar, right? Except the difference is in this case it's all driven by division. And in that case is driven by contractility. And I think that's sort of the key point, right? So that there's some network that is with isolated things that are pulling, where in here it's more of, there's nothing but cells. So I think maybe at some level there really is no distinction. The point is that living systems can set a particular state of stress as a set point. And that state of stress can modulate the contractility of the fibroblasts in this case, or in that case, or in this case over here, it can modulate the rate of division and growth in another tissue. Yes. Exactly. Yep. Yeah. Yeah. That's right. Yeah. Yes. So I think this would be a really nice system to revisit. I'll say what people say about it, what the biologists say about it. But I think now's the time to go back and do experiments on these systems with sort of the insights of modern active matter. But sort of the interpretation of biologists is that each of these little fibroblasts is a little tension sensor, right? And it uses energy, it uses its metabolism to measure how much force is being applied to it, and if that force is too low, it pulls harder. If that force is too high, it pulls less hard, right? And I mean, that's a completely reasonable story, but it sort of begs the question of, well, how does the crosslink know what the state of stress of the continuum is, right? I mean, the cell does not see the continuum. It's just seeing two relatively rigid fibers. It's not obvious to me what the physics is of how you go from how the single cell behavior to the macroscopic thing. So I simply don't know that. But that's the story that the biologists tell. So the rheology of the network, well, okay, so if you sort of, let's say you put in a parallel plates, right, and you let it sit there for a while, you'll get a negative normal force because it pulls. And then if you do the rheology, you'll find it's very, very, very strain stiffening, like super strain stiffening, like even more. It's basically the stresses purport like the constitutive equation that they like to say is that the stress, so not the no, the stress is exponential in the strain. Yeah. So that's actually a standard constitutive relation. So actually, I guess I can pitch one of my papers. So I have a review paper with Humphrey and Martin Schwartz and me, or maybe the author order is that way. I'm in the middle. And the only paper I wrote with two of them, he's a biomedical engineer, he's a cell biologist, I'm me. And yeah, so in that case, Jay wrote a lot of stuff about the rheology of collagen networks, and so there's lots of good references if you're interested more in that. Okay. Yeah. Yeah. Yes. Yeah. Yes. Yeah. Yeah, so excellent question. Okay. So there's a few things to say about that. The first thing is that both the rheology of this in vitro simple system and the inferred rheology from the experiment I told you yesterday inside the cell was power law like rheology. I don't remember if they had the same exponent though, but at least they're both power laws. So there's some connection. But to the other point, though, was more of a point about biology, is of course one cannot say that the actin is like this in the cell, because actin actually has a whole zoo of morphologies. Every morphology of actin that you can imagine exists because there's a huge range of different crosslinkers that make all different types of networks, right? And so presumably. You know, if this well, I should point out that this in vitro experiment, right, was published 7 years before the cell experiment. So it's not like they designed this to describe what was happening in the cell. But if you want to hypothesize that there's a connection between these two, that it would have to be in a place in the cytoplasm where the cross-linking density is relatively low, right? So. That's that. Yeah, so this wouldn't be cortical actin, right? And if I remember, so cortical actin is very, very densely cross-linked, and that's where it's much shorter than the persistence length. But in other, and I think if I remember correctly, they didn't do their measurements in the cortex. They did it more in the bulk of the cell. But I don't remember if they said anything in their later paper about any measurements they made about what the actin in that cell actually looked like. So it's an insightful question that I don't know the whole answer to. Okay, shall we move ahead? Yeah, all right, I'll erase the board. Okay, and now we're gonna go back and talk about metabolism. Or take a few steps back and lots of steps forward. And what I really want to do in the following discussion of metabolism is I want to start off by pointing out some of the complexities of metabolism and then put forth a outrageous simplifying hypothesis and run with it. So that we can make an explicit connection between metabolism and activity as we normally think about it in an active system. So in my last lecture, I defined metabolism, which I will do again briefly, and then I told you about all the many heads of its biological function. So the title of this section is Metabolism from Complex to Simple. And to remind you, the definition of metabolism, actually, someone remind me, what's metabolism? Exactly, yeah, exactly. It's the set of chemical, I'll say, processes that underlie homeostasis. And as I highlighted last time, only a small part of that is physical, right? There's a huge part that's chemical synthesis, of making the molecules of life. And then there's also a ton of metabolism used for information processing and control systems to keep things working properly. Okay, but but now I just want to sort of in a simplistic chemical way, just describe in a simplistic physicist sort of view, describe the chemistry of metabolism and try to make as many simplifying assumptions as I can. Okay. So first thing I'm going to assume that my living system, my cell, is well mixed. Okay, is that a good approximation for a cell? No, it's a horrible approximation. Like every part of the cell has a different chemical composition, but to make any progress whatsoever, just think about things simply, we're just going to assume it's all well mixed. Okay, and so therefore, and this goes along with my idea of a active material, right? In my active materials, it's well mixed, it's homogeneous. Just to keep things simple, the chemical composition is fully described by the concentrations of the components phi I. Okay, so phi is our concentration, I is the index over all the chemicals in the cell, right? So it's from 1 to some very big number. It's not each molecule, it's each species. Okay, so there's going to be a phi I corresponding to water. There's going to be a phi I corresponding to protons. There's going to be a phi I corresponding to everything. Yeah. What I? Yeah. That's a great question, and actually, it allows me to put a plug in for somebody else's book. Okay, so Rob Phillips and a bunch of other people wrote a beautiful book, and it's the idea of the book, the practice of the book, everything about it is beautiful. Okay, it's called Cell Biology by the Numbers by Rob Phillips and a few other people whose names don't stick in my brain. But what makes it especially beautiful is you don't have to buy it. They themselves put it online in a really easily searchable form. So if you just Google Cell Biology by the Numbers, they just basically have tons and tons and tons of awesome chapters on questions like that. How many molecules in a cell are there? And how many different types of proteins are there? What's the concentration of this and that? it's really a wonderful resource if you want to sort of start building physical models of what's happening inside of a cell. Came out a couple years ago. I liked it so much online, I even bought a paper copy because it's really, really fun to flip through. It has lots of beautiful pictures. So the answer is big, but I don't know. Ask Rob Phillips. Yeah. Yeah, that's a good point. Yeah. Yeah. Well, but again, actually, I'm thinking about that, and I actually maybe think that's not even true, unfortunately, because I think in order to get, if you go to a small enough volume where you sort of expect there to be not very many components, I think the absolute numbers of many molecules are so low that using a mean field concentration makes absolutely no sense when there's only one copy. So I think there's sort of it might well, yeah, because yeah, it could be that it depends on the scale of the gradients compared to the absolute scale of the concentrations. My gut is inside of a cell. I'm not sure if you can ever really get away with it, even though there's been many, many, many papers, very highly cited papers assuming this. But I'm trying to build materials in my lab where it meets this requirement beautifully, right? Active materials should meet this. So I guess in the case if you're looking at maybe yeah, if you look at part of this, certain parts of the cell, I'm certain you're like the actin cytoskeleton. I argue that at least pieces of the actin cytoskeleton are like a material, and in that case, yeah, maybe you could get away with that. Okay. All right. So the first thing is there's just a bunch of chemicals, chemical species. And then what the metabolism is, then the metabolism is described by, what are the things we need to know? We need to know the network. So each of those species are the nodes of a network of reactions, okay? So the network of reactions between the components, and then we also know on the edges of that network, you need to specify the stoichiometry of the reactions, stoichiometry of the reactions, and their rates of the reactions, right? Yeah, so it's sort of in the early days of systems biology. Sort of there was a lot of work thinking about sort of chemical reactions on a network this way. And there's a beautiful book by Yuri Alon called Introduction to Systems Biology, where he basically makes these simplifying assumptions and then looks at structural motifs of chemical networks and how they create control loops inside of cells and all that stuff. But I'm not going to get into any of that. Okay, so the metabolism is the list of chemicals, how they react with whom and how quickly, and what that determines, right, is that determines the rate of change of the concentrations, right? So the concentrations of all these things are going to change, and then also, really importantly, it determines the rate of change of all the thermodynamic variables, okay? So there's some density of entropy, right? There's some density of enthalpy, free energy, whatever you want. There's all these densities, okay? And so for each chemical reaction, what's great, the chemists have figured out how to calculate the differences in the thermodynamic parameters for any reaction. And so if you know the rates of reaction and the concentrations, you can calculate how the concentrations are changing. You can also calculate how the thermodynamics, how much entropy are you producing, how much free energy are you consuming. This is what determines your ability to create noise, to drive structural changes in a cell, or to generate work to do in a more ordered case, okay? So that's, simplistically, that's how you would describe it from a chemical viewpoint. Now, again, I like the materials view. I just want to look in steady state. I'm trying to keep simplifying things as much as possible. If we look at steady state, all of the rates of change, all the time derivatives are 0, okay? Right, otherwise, that's the definition of steady state. And so what that implies is that there's got to be a flux. We need, and I mentioned this earlier, you need fluxes at the boundary to keep the concentrations of everything constant, okay? The concentrations and the energies. So there can be, a mass flux. There are mass fluxes, and there are energy fluxes, and there are entropy fluxes at the boundaries, okay? And in steady state, that flux at the boundary perfectly balances all the time rates of chains of these thermodynamic parameters due to the reactions, okay? So, you look at this as an experimentalist, right, or a theorist, as as a physicist where you want simplicity, right? This is a disaster. There's a huge network of the number of components. There's a huge, even more complex network of reactions, and there's fluxes. And what can I measure? What can I measure as an experimentalist? I mean, I could use some really fancy modern microscopy techniques, and I could work really hard and maybe measure the concentration of 1 or 2 components inside of a cell while something's happening, but I can't really appreciate what's happening to the system as a whole, right? So what can I do? What's the easiest thing I can do as an experimentalist? Oh, rheology's good, but it doesn't get to this stuff. That's true, rheology's good, but it's even easier than rheology, actually, at the end of the day. Calorimetry, exactly. I can measure how much heat this active system is creating. It's basically the only thing I can do right now, robustly. So in practice, the simplest and the most general, in that it would work for any metabolism, measure of metabolism is the heat flux. Is the heat flux which you measure through the science of calorimetry. And I'm not going to tell you how calorimetry works. It is a subtle art to do it well. Okay, calorimetry. Okay, and that's just how much heat is coming out of the system. Now, and this is where I'm going to make some connections to Don's lecture from yesterday. So how can we interpret the heat flux? Okay, so there's some things that we know about how we can interpret the heat flux, and then there are also things that we can aspire to know by interpreting the heat flux. So one thing, okay, so and if I have a steady state non-equilibrium system, okay, that is only exchanges heat. Okay, it doesn't have a mass flux going in and out. If it just exchanges heat with the outside world, then the outward flux of heat balances the entropy, how do I want to say it? Due to the internal irreversible processes. Due to internal irreversible processes. Reversible processes. So if I had a living system that I didn't have to feed and didn't produce any waste, then I could directly interpret the heat flux as the entropy production inside of the cell, okay? But they, that's doesn't work for living systems. In an open system, there's another contribution that Don mentioned yesterday. And an open system, and by an open system I mean one that can exchange mass as well as heat with the outside world. The mass flux also carries entropy, right? So you can get rid of the entropy that you're producing, because in steady state, you have to have a constant amount of entropy in your system in steady state. Your irreversible processes produce entropy. You have two options for getting rid of entropy. One is to shed heat, okay, and that's the easiest one to do. That's the easy one to measure, and that's the easiest thing to measure. But you can also, if the waste of the reaction has a higher entropy than the fuel, then you also get rid of entropy by rejecting matter to the outside world. Okay. Let me say, put a plug in for another book that I didn't write. I've never written a book, probably never will. Another fabulous book. How many of you know this book? Who wrote it? Yeah, good old Irvin, right? Wrote this book. Anybody know what year? Yeah, 1940. Is it 44? Was it still during the war? Oh, really? Wow. I think I had 47 in my notes. I'll just put 40x. Yeah. So, yeah, it's interesting. I mean, it's sort of. It's a beautiful essay. It's a mini book, long essay, and it talks about all sorts of things, and it really grapples with a lot of these questions inside of it. And I highly recommend that you read it. Almost as fun as Robert Brown. And I'll say a little bit more about that book later on.